The one that involves a single component system. That's the first example we looked at. And then today we're going to look at one that involves two components under steady state conditions. And the third one that we're here to look at is the one that is a system that includes steady and non-steady state conditions. Okay, so we looked at this. We looked at these equations, try to understand this graph. I hope we remember our discussions from this graph. That going forward, when the beaker is full, what happens? FL becomes equal to FI. Very important. Okay, so we continue to look at steady state. So we're going to look at a problem now here that involves a system that is under steady state. It indicates right here in your question. I hope I'm audible to everyone. Are you able to get me clearly? Can I just get one yes and I continue?
Yes, we are.
Great. So the question says, calculate the pollutant concentration. I want you to imagine this very, very well with me. I'll be slow in my explanation also. Calculate the pollutant concentration in a lake that receives wastewater from two factories. So imagine there's a lake, and this lake receives two Okay, so it receives wastewater from two factories, two separate factories. The lake surface area is 1 square kilometer with a depth of 3.3 meters. With a depth of 3.3 meters. Okay. The lake is also fed by a river with a flow rate of 10,000 cubic meters per day. And the two factories are discharging a certain inert pollutant X into the lake. Okay, then you've been given here the parameters, the flow rate. So for factory 1, it's discharging pollutant concentration into the lake at this flow rate, 1,000 cubic meters per day. And the concentration of pollutant X, we're calling it X1 in this case, is 85 milligrams per liter. Okay, coming to factory 2, the flow rates are 150 meters squared per day. So these are volumetric flow rates, and the concentration for pollutant X, so they are both polluting with pollutant X. So pollutant X for factory 2, we'll call it CX2, is 375 milligrams per liter. That's the concentration. So what's the question asking us now? The question is asking us to calculate the pollutant concentration in a lake that receives wastewater from two factories. So you have a lake that is receiving wastewater from these two factories. Okay, so you have a lake with you here, and it's receiving, so you have a factory here. Okay, so you have factory 1 here, F1. Okay, then you have another factory here, which we are calling F2. Okay, so both these factories are emitting what? Effluent into our lake. Okay. And these are the rates, the flow rates are given here. Okay, so let's move down and see what else. Okay, so an inert substance does not absorb or settle. Remember, we've been told that the gas is inert, so meaning that we're now just being given a brief explanation of what an inert gas really, what properties it has. It does not absorb, settle, or evaporate, or is in any other way involved in any kind of physical or biochemical reaction. Okay, so this is going to help us in our mass balance analysis, okay, trying to understand where this pollutant is going. So we're told it will not absorb. I hope you still remember what adsorption is. So it does not absorb, it does not settle, it does not evaporate, or is in any other way involved in any kind of physical or biochemical reaction. So it's not involved in any reaction, that's inert. So it's just basically what it is, okay? It's there and it's not doing anything. It's one chemical that will not react anywhere and whatnot. So to calculate the concentration of a pollutant X in the lake, a mass balance is formulated. Okay, so since it's similar to what I drew, let's look at this. Okay, so ignore this one for now. So what do we have here? We have our lake, okay? And then we have factory 1 and factory 2. Okay, so aside from that, we're told that there is actually a river. The lake is also fed by a river with these flow rates. I forgot to indicate that, so let's indicate that one also. So we have a river there, okay, with a flow rate Fi. Okay, so there are three flows, okay, three influence to this lake. There's effluent from F1, factory 1, effluent from factory 2, and a river also that is flowing and feeding into this lake. That is what we are told. Okay, so let's move further. So we're now trying to define our system boundary. So where's our system boundary? Basically, the boundary of this lake. Okay, so the lake now becomes our reactor. Okay, so this is where everything is happening here. This is where the mixing now of what's coming from the river, what's coming from factory 1, and what's coming from factory 2. And then we're told also that this lake is not just filling up, but but it also has an outlet here. So there's an inlet, 3 inlets, and 1 outlet there. Okay, so summation of Mi, which is inlets, mass at inlet will be this one plus this one plus this one. And the summation of Ml will just be simply this mass that is leaving here. Okay, so we look at the balance, we look at the equation now. Okay, so we look now here, what do we have? Mass balance equation. So for pollutant X, we had this formula earlier on. So dVc X over dt. So change in what? In volume multiplied by concentration over a change in time is giving us what? Flow rate for the river multiplied by the concentration of pollutant X in the river plus a multiplication or a product of volumetric flow rates for factory 1 and pollutant X concentration in factory 1 effluents plus volumetric flow rate for factory 2 multiplied by concentration of pollutant X from factory 2 minus what's leaving. So this is a summation of what? Mi. This is summation of Mi minus summation of ML plus production. Okay, so there's something more in detail here to help us understand. So accumulated, so we're trying to basically understand accumulation, okay, which is dV. So this is the volume of the lake, okay, multiplied by the concentration of X in the lake over time. That is exactly what accumulation in this particular place is. in our reactor at the moment. So it's dVc over dt. So over time, we'll have that happening. So maybe can I have someone help us understand why we have dx at the bottom there? Why are we considering time? Simple explanation why we're considering time in this equation. Just so I know that you're understanding. Mr. Joshua. Okay, yeah, you can go ahead.
There's variation in time.
Mm-hmm.
The time, let's say we have the first of the person coming in. So over time, there's that accumulation of changes with the reactant of the acid. Because the echo is coming into everything is happening over time.
Okay, so at T is equal to 0, what is the concentration of pollutant X in the lake? So at T is equal to 0, provided that these factories will be discharging at the same time, it means that the concentration of pollutant X in the lake is 0. Okay, so the lake is only receiving this pollutant after effluent starts flowing through into the lake. So the lake without the effluent from factory 1 and 2 actually has 0 pollutants X. Coming to the river, I don't think we're told in the question. Let's come back to the question. The question just tells us that, it just gives us the flow rate of the river, which is 10,000 cubic meters per day. It's not, so meaning from what we've been given, since there's information missing on the pollutant X in the river, it means that we assume that the river has 0 concentration of pollutant X. So what we have is this mixing with this, isn't it? These concentrations mixing together in this given volume, which is our dVc over time. So over time, so T is equal to 0, you have concentration equal to 0. Let's say when T is equal to 5 seconds, what happens? There's going to be 0.00 something concentration of pollutant X entering the lake. And then over time, that concentration will begin to increase and increase and increase. So that is now what we're trying to analyze here. So from our equation here, we've been told, so the equation, our working equation for mass balance is what? What's coming in minus what's leaving plus production. That is our accumulation. That is our accumulation. So it's the same thing that we're trying to understand here. So what's coming in, we factored in what's coming in from the river, what's coming in from the factory 1, and what's coming in from factory 2 minus what's leaving the lake plus production. Okay, so now we've dealt with pollutant X. This is the mass balance that we're going to use, equation that we're going to work with. So coming to just water. So remember that aside from pollutant X, there's also water coming in. So that what's coming in from the factory is also water, is a mixture of water and pollutant X. Okay, so that will be change in density of water multiplied by volume of the lake over change in time. So it means that apart from the concentration of pollutant X, the other thing that is changing in that lake is actually the volume of water, isn't it? So the volume of water is increasing over time. So how do we put that in the equation? This now becomes our working equation. So this becomes rho, meaning density of water. So rho multiplied by volumetric flow of the river plus rho multiplied by volumetric flow of factory 1 plus rho multiplied by volumetric flow factory 2 minus rho, which is still the density of water multiplied by the mass flow rate, the volumetric flow rates of the outlets plus production. Okay, so how do we understand it further here? So basically, we're trying to understand the accumulated water mass. So we're saying the water that came in minus the water that is leaving through these outlets, plus any production, if any, of water in this reactor. In this case, our reactor is the lake. That is basically what we're trying to establish here. Maybe I'll pause a bit and just leave room for questions in case I'm too fast for someone. I'm willing to go back and explain. Do you have any questions at this point?
Yes,
Okay.
on
Pardon?
the mass balance for the pollutant where for the pollutant takes. Yeah, I
Sorry.
did not get the point where you mentioned change in time is 0.
Or I was trying to give an example to say
I did not get the.
Okay. Okay. Let me try and explain. So I mentioned time where time is equal to 0. I was trying to help you maybe understand. So I asked. So meaning at the beginning, before, in short, time is 0 before you have these all these flow rates, okay, these effluents entering your lake. We're calling that time 0, okay, before any of these begin to enter the lake. So before any of these begin to enter the lake, any of these concentrations of pollutant X begin to enter the lake, it means that the lake is free of pollutant X. In short, there is 0 concentration of pollutant X. Then with time, okay, when you now begin to discharge these effluents into the lake, time is moving, isn't it? So initially, with time, what happens? The concentration will be much lower, right? But then as time passes, what happens? These flow rates are constant, right? But over time, the concentration now of pollutant X will begin to increase and increase and increase in that lake. That is the understanding there behind. I don't know if I've answered your question. So meaning if it's integration, you have if it's a limit, isn't it? You have t is equal to 0. And for example, if we're told up to when this lake was being filled by this effluent. So if they say maybe they filled it for an hour. So the limit for our integration would be what? T is equal to 60 minutes at the top, and then at the bottom you have 0. So at the top you have 60 minutes, at the bottom you have 0 in integration. Any other questions? Okay, we'll move forward. So coming to water, this is how it looks like. Okay, so you have what's coming in, the water that's coming in, minus the water that's leaving, plus production, mass of produced water in the reactor. Then now we come to assumptions. What assumptions are we going to make for our system? So we start with the lake. What's the assumption? The assumption is that the lake is fully mixed. There's homogeneous distribution of dissolved substances. Okay, so meaning as these pollutants are entering, what's happening? There's mixing, isn't it? Homogeneous distribution of pollutant X in that lake. In reality, does that happen? No. Does that make our equations easier to solve? Yes. B, it has a constant volume. Do we agree?
Yes, we do agree,
We
madam.
agree, isn't it? So meaning a cup will remain with a constant volume, isn't it? Whether or not you overflow things in there or you just put halfway, the volume of the cup still remains constant. So same thing as here, the lake does not expand to accommodate more water. No, its volume will remain constant. So meaning dV over dt is equal to 0, very important. This is how we know that this is a steady flow equation, because our dV over dt is equal to 0. Okay, change in volume over change in time gives us 0. So it means that volume here is constant even over time. It remains constant. The third assumption here is that water density is constant. Okay, so the density of water remains constant. It will not change. Okay, so meaning probably it will not change because the temperature also probably is going to be the same. But anyway, we're just interested in density at the moment. The fourth assumption under lake is that it has no production of water within the lake. That is, so there's some typos here in these notes. Please take note. There's supposed to be a T here. That is, P is equal to 0, meaning there is no reaction in the lake that is producing more of water other than the water that's entering from the influence, and other than the influence water. That's about the lake. So we come to the mass balance. We looked at this, isn't it? So mass balance for water. So FL, which is the outlet, will be composed of what? The flow rates that from the river, the factory, and factory 1 and factory 2. Okay. So we looked at this already. This equation, we looked at it in detail already. Okay. Then something here interesting happens. So dV over dt. Remember we said that dV over dt is equal to 0, right? So it means volume is constant. So what is this volume? So meaning Fi plus F1 plus F2 minus FL will give us 0. Okay? We're borrowing this from here. So this gives us 0. The river water entering the lake, which is Fi, does not contain pollutant X. That is, so if it does not contain pollutant X, let's come here. So it means that this equation, so this is for the river, this is for factory 1, and this is for factory 2, and this is for the outlet. So meaning if concentration of pollutant X in the river is 0, it means that Fi times 0 give us what? 0. So automatically this will give us a 0 value here. That's what is being explained here in the assumptions. So the river water entering the lake does not contain X, that is, this is equal to 0. There's no production of X in the lake. And there are steady state conditions with respect to X and with respect to water. So we have those equations there. Okay. Then if steady state conditions means that change over volume times X over change in time, this will also give us what? 0. Okay, so 0 will be equal to, we said already this is giving us 0 because there is no pollutant X in the lake. I mean in the river, sorry, coming in from the river. So you have 0 here, plus this value will be a positive value, this will be a positive value, this will be a positive value, plus 0. Why is 0 here at the end? Because production of X, there's no production of water in the lake. So our P there will be equal to 0. So that's why we have the plus 0 here at the end. The solution derived from the above assumptions and arguments is that CXL will give us this.
Madam, sorry, I have a question. On you say the PX is equal to 0.
Yes.
And then in your explanation, you said PX is equal to 0 because there is no production of water in the system.
Yes.
Is it production of water or concentration of the pollutant?
Oh, sorry. Yes, sorry. PX, you're right. Thank you for that correction. PX here is indicating production of the pollutant in the lake. Thank you for that correction. Okay, so meaning there's no production of pollutant X within the lake. Hence, we have a 0 here. Okay, so our question was asking us what? To find, let's come back to our question just quickly so that we look at it together. and understand it again. Calculate the pollutant concentration in a lake that receives water from 2 factories. So you're asked to find what? The pollutant concentration in the lake, isn't it? Okay, so now let's come back here and try and remember something that we looked at last time we met. So how do we find concentration of the lake from here? Which one is telling us, giving us a picture of the actual concentration in the lake? So this has been picked, CXL. Do we understand? Maybe can someone briefly explain why we picked this one? Outlet concentration.
Maybe I can try.
Please.
Yeah, the CXL is the concentration of the pollutant that is leaving the lake. Maybe that's why it's peak.
Okay, anyone else who has a question, who's wondering why we picked this one? Have we understood? Have we all understood? No need to explain why we picked CXL. Okay.
No, madam.
Okay. So the question is asking us to find the concentration of pollutant X in the lake, isn't it? But then we have picked the concentration of pollutant X on the outlet. Why? Because based on what we even covered yesterday, last time we made, we gave an example to say, okay, if you are walking Bolenda and you're carrying what juice? Okay, let's say you're carrying Fruticana mango, okay, in a cup. And as you are walking with this full cup of Fruticana mango, you kind of stumble on a rock or something, you trip, you buntula yourself, right, as we say. So now when you buntula yourself and you find that some of that Fruticana spills from your cup, okay, it's now on the floor, like half of it is on the floor. What do you think? The concentration of the Fruticana that remained in the cup, is it the same as the concentration of the Fruticana that is on the floor? Okay, you're walking with tea, with a cup of tea, and then you trip somewhere, and then you spill some of that tea from your cup. The concentration of sugar in the cup, is it the same as the concentration of sugar in that spilled tea that is on the floor? Are they the same or they're different?
Good evening,
They are the
madam.
same, madam.
They're the same.
They're the same, isn't it? Or Olimbi, the one
Yes.
that spills yellow Loesha.
I think the best example is the one you explained last time,
Okay.
where you were saying, let's say you have water in a glass, then you start putting juice in there bit by bit. Then you ask the question to say, do you think they will reach a certain point where the concentration of juice in that package will be equal to the concentration of juice in the glass? I think this is the same principle we are going to adopt here.
Yes, exactly.
So the concentration, as they are coming into this lake from factories, they'll result into FLCL.
Thank you very much for that also. So meaning for us to have outlet, isn't it? It means that that lake is full, isn't it, at some point? Okay. And so the condition that we've set for ourselves is that there's homogeneous mixing. Okay, so as those pollutants are coming in, they're mixed everywhere. So meaning even on one end, the concentration will be the same, which in reality, like I said, is not the same. Okay, so our assumption when we say it's homogeneously mixed is what we mean. We mean that as soon as these enter here, right, there's going to be homogeneous mixing. Mean the concentration of pollutant X at this point will be the same as the pollutant X at this point. Okay, same as this point and everywhere else in this lake. That's the assumption, such that whatever is inside, concentration will be the same as what's overflowing, what's leaving here as our FL here, CL. It will be the same. That's what we're trying to do here. So that's why we're picking on outlet concentration, because we know that outlet concentration in this case is going to be the same as concentration within the lake. Okay, so it's from this formula that we solve for our CXL here. So we have CXL on this side. Okay, then what remains? F1 CX1, which is this one, plus F2 CX2, which is this one. So as you can see, this is another typo. Okay, so this minus is not supposed to be there. This is what is supposed to be here. It's supposed to be F2 CX2. So it's supposed to basically ignore this. It's not supposed to be there. Okay, same as here. This is supposed to be ignored. This is a typo. All right, so you have F1 CX1 plus F2 CX2 divided by FL. So what do you have here? You know this volumetric flow rate for factory 1. You were given the concentration, which was 85 milligrams per liter in the question. Okay, plus F2, you were given volumetric flow rate for factory 2. And you're given the concentration for pollutant X from factory 2 there. Divided by FL. So now what is our FL? FL is equal to what? We defined this already. FL is equal to Fi plus F1 plus F2. Okay, why are we using this principle? Remember what we said earlier on also. So when your cup is full, okay, for us to have an outlet, it means that there's overflow, isn't it? So for this overflow to happen, it means that what's coming in will be equal, basically, in terms of flow rate, to be equal to what's leaving. That's the same principle we're having here. So meaning, what's coming in, which is Fi plus F1 plus F2, is equal to this rate. So the rate will basically be the same. So that's why we have our Fi. Okay, we're not given this flow rate, but we're given these three. So meaning we use these three to find this one. That's why we have 10,000 here, cubic meters per day, plus 1,000 cubic meters per day, plus 150 cubic meters per day. And when everything is multiplied and added and divided accordingly, our final answer will be 13 milligrams per liter. Okay. So in an exam, this question will carry 20 marks, or in a test, it carries 20 marks, the full question. Okay, so what's important is just to basically understand and hear. That's why I really wanted to make sure that you understood why we picked this one, because I think this is where most students get a bit confused. Okay, trying to derive and trying to understand what exactly are we solving for and how are we going to get it. So if you're asked to find pollutant concentration in the lake, you are picking this one. At least I hope we've all understood why. Okay, so sorry, unfortunately my Zoom is still 40 minutes, so we'll be signing out like in about a minute. We're all going to be logged out, so you just simply log in using the same link. Okay, we're done with this question. Can I have questions from those who have not understood? If you're not clear, kindly tell me where you're not clear so that we repeat. Okay, I'll take it that we're all clear. Either we're all clear or no one is clear. Silence means that we're all clear or no one is clear. I'll take it we're all clear. Okay. So let's look at this here. Observations. Mass balance analysis can be used for further study of the system. Compare the actual concentrations measured with the calculated concentrations. Check whether they match. If measured concentration differs from calculated one, reassess the validity of the assumption. So what they're trying to tell us is that you can also simply just get the outlet concentration, isn't it? You can measure it. And if you find that it matches this one, you still get 13. It means that your mass balance is correct. But if you get another answer other than this, it could mean that there's somewhere where you may have missed it, sorry. Or it could mean that some of the assumptions are not holding true in your particular case. So you have to go back. Okay, so the question that you'll be asking yourself is that, is the substance X really inert? Maybe it's actually